I'm going to leave these next couple of pages because we usually do the exponential. We study the chapter on the exponential before doing logs. However, this time it was suggested that we change the order. Now, since we've changed the order, I'll have to talk about some of this stuff is now because we haven't talked about the significance of E. It means more than just exponential, but you will find that in the later chapter. Now, so because we haven't done that chapter, I will just go straight to 12b and talk about the significance of the connection between exponentials and logs after or during the exponential chapter. So, exercise 12b, the log function and its derivative. So you're going to see here that to differentiate a log function, we call it the log function. Then there really is only one base that we consider the derivative of the log function to, and that is base E. Now, this is all a bit awkward because, like I've just said, we haven't studied the exponential, which is, again, identifying what this E is. Hopefully you can just accept at this stage E is a really special number. It's just a really special number. It's between 2 and 3. If you are to take your calculator, just see if I can pick the calculator up, bring it into the view of the screen. Okay, there you go. From your calculator, E to the power 1 is this number, 2.71828, blah. How did I bring that up? See E to the x here, it's above the log function. Again, indicating there's some pretty significant link between E to the x and log of x. And I just press second function, this button, and I put a 1 in for the power, and this number came up. So yes, it is a number. It is a number between 2 and 3. Like I said before, really, really significant. Not so much to do with logs, more so to do with the exponential, and you'll learn more about why it is so significant when we do that there. But when we talk about the calculus of the log function, there is only one base that we study the derivative of, and that is when the base of the log is this number E, this 2.7183, blah, blah. So our definition for the derivative of log to base E is that it is 1 on x, 1 on whatever is going on here. So we've got log of something to base E. Its derivative is 1 over whatever that something is. So over here, again, we're just saying if y is equal to the log to base E of x, then the derivative, d dx, of this is 1 over x, or just a different notation, y dash is 1 on x. So what do you notice? I hope you notice that its derivative looks nothing like its original form. Nothing like it. The original function written back here that we differentiated actually had the letters log written in them. It actually was a log function. What appears in the derivative has no reference to logs. So the derivative of the log function goes to a simple little fraction. That is so significant, so significant. We've not had that sort of thing happen before. And you won't in the future. When we differentiate an exponential function, you'll see a lot of similarity. When we differentiate a trig function, you'll see a trig function. However, in this case, when you differentiate the log function, the result looks nothing like a log. In fact, it's a fraction. This box here is just saying that if this is more than simply x, so it might be x squared or x cubed plus x squared, something that constitutes its own little function in x, then the derivative of the whole thing is 1 over that, and I'll talk about the second part first, because that's the easiest part to write down. It's always 1 over the function. 1 over the value in this position. So if it's x squared plus 3 here, or 3x, it's x squared plus 3x here, 1 over x squared plus 3x. Then you multiply by the derivative of this. So, yeah, that looks like something that we're quite familiar with, called the function of a function rule. Let's have a look at these examples. We're differentiating x plus log to base e of 2x. Now, we've got two terms being separated. There was a rule very, very early on in differentiation that said that if you've got this situation, you differentiate x separate and then differentiate this term. So differentiating x, it's got nothing to do with logs. So the derivative of x, we use our previous rule, and, that just becomes 1. Bring the power to the front, subtract 1 from the power. And now we have plus log to base e of 2x. It will definitely be 1 over 2x. It's always 1 over whatever sits in this position. This will require the function of a function rule, and the derivative of 2x is 2. If I just scroll back a little bit, oops, wrong way. You have to differentiate your little function in x. The derivative of 2x is 2, and it goes here, the front. We could simplify that a bit. We could cancel out these 2's, and we've got 1 plus 1 on x. You might see that written with a common denominator, and to get a denominator of x, I'd need to multiply this by x on x. Got my common denominator. The numerator there for this part of the fraction would be an x plus 1. So you might see the derivative written like that. With this next one, d dx, this one is a very nice example of the rule here, because we're differentiating a log function that is in itself a function in x. So the derivative of the log is always 1 over. Now you can see that I've moved over a little because I know that I'm going to have to multiply by the derivative of the x part. And to get that, we treat it just like we've treated all our previous derivatives. Bring the power to the front, subtract 1 from the power, and so on. So we get 15x squared plus 3. And I would bracket that because it's that term being multiplied. You might see that written as 1 complete fraction. And you would simplify your fraction if it was possible, but it's not possible in this case. With the next one, the derivative d dx of the log to base e of 5x plus 1 plus x squared is similar to this situation. We had two separate terms. Again, we've got two separate terms. And so to differentiate those, we can think of them as differentiating them separately. The log of this, we're going to definitely put 1 over 5x plus 1. But we know that we will multiply it because it's a little function in x. Using this rule here, we will multiply it by the derivative, which is 5. We're moving on now. Differentiating x squared, we just use the previous rule. Bring the power to the front, subtract 1 from the power. So we'd have 5 on 5x plus 1 plus 2x. Now, you could see that written with a common denominator, and again, that will just be up to the textbook or whatever. And to get the common denominator, you would multiply this by 1, which is all you can do. You don't want to change its value in any way, so just multiply by 1. You'd get your 5x plus 1 as your common denominator, and you'd have 5 times 2x outside of 5x plus 1. And what's that? 5 plus 10x squared plus 2x all over 5x plus 1. Don't know if that could be factorised. If you could factorise that, you could even end up crossing out your denominator. In the next one. Now, this is a function of a function. We have to deal with the bracket to the power 5, just like we had always previously dealt with a bracket. So our differentiation rules from the previous chapters still apply. So the derivative now of, with respect to x, of 1 plus log to base e of x all to the 5 becomes, I bring the 5 to the front, 1 plus, and I don't change this at all, but I do subtract 1 from the power. I then have to multiply by the derivative of what is inside here. Now, the derivative of 1 is 0. I'm not going to put that in. The derivative of log of x is simply 1 on x. And so you might see that written as 5 times 1 plus log to base e of x to the power 4, all on x. I'll stop the video there and talk about the rest of the examples in another video.